Hello class, this is section 7.2 and in this video we are going to discuss higher dimensional product solutions. Let's consider the vibrating membrane equation, although everything we say in this video will apply to the higher dimensional heat equation as well. And we're going to ignore the boundary conditions for now, even though there will be boundary conditions in a vibrating membrane equation. You can think of this equation as calculating the movement of a trampoline. Now, we can perform a similar trick as we did in one dimension, that is, find product solutions, and these are going to be of the form u, x, y, t, and we separate out the space variables, f, x, y, from the time variable, gt, just as we did before. So when we plug these in, let's see what happens. And once more, we can pull out constant terms, like in the left side, fxy is constant with respect to t, so we can pull that out, and we are left with this. So we have fxy, second derivative of g, equals c squared gt times the Laplacian of f. And we can perform a similar trick, of course. We want to move all the g's to the left and all the f's to the right, all the space variables to the right. And this gives us 1 over gt partial squared, d squared, dt squared of gt equals to 1 over fxy times the Laplacian of f, partial x squared plus d squared fxy partial of y squared. Now these should be partials, not these. Alright, and a similar principle holds. The left-hand side is independent of x and y, and the right-hand side doesn't depend on t. Since they are both equal, both sides must not depend on x, y, or t, and therefore they must be a constant, and that's called the constant minus lambda. And we picked the minus sign again because we want the eigenvalue problem to look a proper way. So this reduces to our two equations. First, an ordinary differential equation in G, and this is one that's pretty simple. You know how to solve this already, and we've done this several times, not just in ODEs, but also in this course. And we also get this equation. So this is an analog of our normal eigenvalue problem, except with the Laplacian replacing the second derivative. So notice that this second eigenvalue problem is going to be a PDE instead of an ODE, which is going to be problematic, but I think it's also clear that this eigenvalue problem is still a lot easier than the problem we started out with. So to solve these higher dimensional partial differential equation problems, like the vibrating membrane problem, we have to think about how to solve higher dimensional eigenvalue problems, and this will be the subject of a future video. Oh, and I just realized I've forgotten the c squared. It should go here, and there should be a c squared here. But no big deal. Sorry about that.